Hey, good morning, everybody. So, want to take you guys back into the lab. And over the last couple days, we've been talking about a lot of different things we can do to measure gases, both at STP and at non-STP conditions, right? So, the non-STP setup, we use the ideal gas equation, all right, to generate a lot of what we want to learn about the gas, which we will continue to use today. At STP, we use brackets to obtain whatever the label is of what we're trying to measure. So the goal of today's lab is we want to calculate a gas's molar volume. So molar volume comes in three flavors, right? Liters per mole, milliliters per mole, or cubic centimeters per mole. And don't forget, those guys are the same. All right, so if we were listing the goal of this lab, the molar volume of the gas lab that we are trying to do is we are trying to create, collect, and determine the molar volume of hydrogen. So we want to get for the gas we create is the liters of it per moles of it. All right, so first thing we got to do is we have to create, all right, the gas. That's easy enough. We've done this reaction a number of different ways now, but one of the hallmarks of reactions is if you take a metal plus an acid, you will get, all right, hydrogen gas, released as long as the metal is quote unquote active. So today's metal is magnesium. We're going to take a strip of magnesium ribbon and we're going to react it with 2 molar hydrochloric acid. All right, so if we took a look at this, it'd be a single replacement. The magnesium would kick out the hydrogen in the hydrogen chloride. So we end up getting magnesium chloride plus hydrogen. All right, if we wrote and balanced the equation for that guy, right, magnesium, one word, not a Hoberwinkel, hydrochloric acid, hydrogen chloride, H is +1, Cl is -1, magnesium chloride, Mg is +2, Cl is -1, so we cross those down, we get MgCl2. And last but not least, hydrogen, one word, is a Hoover. And then you'd scan, you'd see our Cls aren't balanced, so we put a 2 there, and that takes care of everything else. And then the part I tend to fill in for you guys, just because you're not as familiar with it. All right, so magnesium's a metal. It's going to be in ribbon form, so it's a salt. Like the HCl is an acid. It's aqueous. That means it's dissolved in water. The MgCl2 is also aqueous, which means it's going to dissolve in water. And my H2 is the gas that I'm going to create. Right, so what we're going to do is take a little strip of magnesium ribbon, right, and we are going to put it in the presence of hydrochloric acid. The only difference between this and the other labs that we did was last time I just generically collected the hydrogen in a bottle. I didn't care how much hydrogen that we'd got. Today, we very much so need to know how much hydrogen we gather because I want to measure the liters of it. So there's 2 facets to what's going on. Right? The first part of what's going on is how do we get the liters of hydrogen? So what you're going to do is you're going to take a gas collection tube, and at the very top, you're going to put some HCl. Right, then we're going to put a whole bunch of water in the tube. And then at the bottom of the tube, we're going to put a cork. And we're going to put a piece of copper wire that has our magnesium on it. and we're going to hook that up underneath. So then what we're going to do is it's going to let the HCl come down, react with the magnesium. We're going to create hydrogen, which will go up here because it's not very dense, and it's going to push the water around and through the cork at the bottom. So at the end of the day, what you're going to have is this gas collection tube. It's going to have a lot of hydrogen gas in it, but because we're collecting over water, it's going to be a little bit of water vapor in there as well. So you're going to see a lot of the ideas we've been talking about in the last chapter. We're going to be collecting over water, so we're going to have to look at a Dalton's law problem when we calculate pressure, right? Because the barometer is going to tell me the total pressure of these two. I'm going to have to remove the vapor pressure of the water. We're going to use the tube itself to measure the volume. So they'll just be readings. So over here, this will give us our milliliters of the H2. And even though the H2O accounts for some of the pressure, most of the measurement you'll find out of the volume is coming from the hydrogen. All right, so what I want to do is walk you guys to the back, all right, talk you through the experiment, start collecting our hydrogen. And then what I'll do to help you guys out, because this is a more high-level lab, is I'm going to post a separate video, right, of how we want to attack some of these problems, because this is one I tend to help a fair amount with in class, just because there's a lot of different ideas. All right, but the first thing we want to do is conduct our experiment, generate our gas, and see what we're working with number-wise. All right, so I'm going to grab my procedure and my goggles. Plug you guys and take you to the back. Let's set you guys up top like I usually do. All right, and what you guys will see at your counter, all right, so we'll have our ring stand with a double burette clamp. All right, and that double burette clamp is designed for holding our gas collection tube. Okay. All right. Now, what I need to do is I need to prep my tube. So if you look and follow along in your procedure, first thing it tells us to do is fill up a 400 milliliter beaker of water, about 3/4 filled with water. Right, so you go in your drawer, your second biggest beaker is your 400. We're going to fill it 3/4 full of water. So we're putting about 300 milliliters of water in like that. All right, now it says obtain or cut a 4.5 centimeter piece of magnesium ribbon. That would be a procedural change for us. Over the past few years, I found out that generates just a little bit too much gas for us. So what we're going to do is we're going to measure out 3 centimeters. All right, so I'm going to snag a pair of scissors. And if I take out my magnesium ribbon, it's nothing crazy. Right, shiny. Right, silvery looking. Sometimes you'll get a little black coating on the outside. That means it's oxidized. But when I was in the back, when I grabbed this, I just took a little steel wool to it to make sure that it was nice and clean. All right, so we go in our drawer. We get our centimeter ruler. And we're going to measure out a piece 3 centimeters in length. And we're going to cut right there. Okay. Now, you want to try to make sure you have a nice flat edge on that, because if it were curved like this, you wouldn't be getting all of it. You'd be missing magnesium from that process. Then what I'm going to do is I'm going to come over to the middle counter. I'm going to grab a piece of wire and a cork. So I'm going to get my copper wire, which is what I'm going to tie my magnesium ribbon to, my cork for the bottom of my gas collection tube. All right, and then it tells me, get a piece of copper wire, 15 centimeters, twist and fold the magnesium wire around it so that it can't fall off, which means we want it to look like this. And so you can see the magnesium on top of the wire, right, so that the acid will fall on it and be able to react. All right, then we need to prep our gas collection tube. So I'm going to go into my drawer and I'm going to get my graduated cylinder, right? And then it tells me to get 15 milliliters of 2 molar hydrochloric acid. So I'm going to come over here and I'm going to measure that. Nothing crazy. Just pour it in. And here's my 15 milliliters of my acid. So I'm going to take this guy, put him down in the sink. I'm going to pour him. And right now, what I have is 15 milliliters of acid down there. And I don't want it to get to my magnesium ribbon, right away. So I'm going to take some of the water from my beaker, and I'm going to fill this guy up the rest of the way with acid. And it's okay if it overflows a little bit. And so our whole tube's filled to the top with the water now. So now I've got water in here and acid. All right, now I'm going to take my ribbon with my magnesium. I'm going to insert it like this. So now you can see it's in there. And now I'm going to take my cork. I'm going to cap the end of this. All right, and this guy's ready to react. The acid's down here. The metal's up here. So what I'm going to do is I'm going to flip this guy over. And I'm going to plunge him into the water just to equalize our pressure so my cork doesn't pop out. And then what we'll do is we'll see what's happening with our reaction. So I'm going to flip this guy over, and nothing needs to be done super fast. Take my time. Move my beaker to where I can get my tube in. All right, and if you look close, you can see the acid making its way down. Okay, but I'm going to put you guys down here at ground level. I'm going to turn my beaker so you can see inside. And pretty soon, you guys are going to start to see some bubbles, all right, fizzing, right, as the hydrogen gas is getting generated. All right, and there's nothing too crazy there. You'll just see those bubbles. So what I'm going to do while that's going on is I'm going to take you guys back up front, and I'm going to walk you through some of the pre-lab questions together, all right, to give you an idea. And the pre-lab and the post-lab are very, very directly related. All right, so I'm going to walk you through all my pre-lab calculations so that when we get our post-lab numbers, you guys know what to do. All right, so if we head to the pre-lab, which is on page number 3, you'll see there's 4 pre-lab questions, and they're giving us, all right, some information. The first bit of info they give us is what the strip of magnesium ribbon weighed, right? And ours was in centimeters because we measured it and it would be too light to record on our balance. So I'll show you in the post lab how we will get that particular one. All right, so if we look at the pre-lab, it says a reaction of 0.028 grams of magnesium with an excess of hydrochloric acid generated 31 milliliters of hydrogen gas. All right, so we know we have 0.028 grams of magnesium. We also know we had 31.0 milliliters of hydrogen gas collected, and that was not at STP, right? The lab conditions for us were 22 degrees Celsius, and they're telling me the barometer read 746 mmHg. And remember, the barometer is the total pressure. That isn't necessarily your hydrogen gas, because some of it's the water vapor that we were talking about. All right, so if you look at number 1, it says use Dalton's law and the vapor pressure of water at 22 degrees, which is in the table immediately above, to get the pressure of the hydrogen gas in the tube. All right, so in pre-lab number 1, what we're looking at is a Dalton's law problem. P total is equal to the pressure of the hydrogen plus the water vapor. The barometer tells me the total pressure. So my barometer is 746 millimeters of mercury. I want my hydrogen. And I would need to know my water vapor pressure. Well, you have this table right up above. And if we scan at 22 degrees, it tells me that water contributes 19.8 millimeters of mercury for that temperature. Right, so all we need to do is our subtraction, all right, to get the pH 2 by itself. So we take our 746 minus our 19.8. Right, the 746 stops at the decimal, so our answer must, which means we're looking at 726 mmHg. Okay, all right, then we're on to question 2. All right, question 2, it says, use the combined gas law to calculate the corrected volume of hydrogen at STP. And it says, watch your units for temperature and pressure. All right, so if we want to get our volume of hydrogen gas at STP and not at our conditions, we can convert it. It said use the combined gas law. All right, so combined gas law is P1, V1, T2 equals P2, V2, T1. All right, so we want to know what would our 31 milliliters be worth if it were at STP. All right, so we have our initial conditions. All right, it's the 31 milliliters, it's the 22, and we knew the gas was 760 mmHg. We want to know what's the volume at the end. So we're looking for the corrected volume, so we want V2. So if I rearrange that, I get V2 is equal to P1, V1, T2 over P2, T1. So like I said, we know our initial conditions. Our initial pressure was the 726. Our initial volume is the 31 milliliters. Final temp, we didn't talk yet, but we will. Final pressure, we didn't talk yet, but we will. And our initial temp, we know, is the 22 degrees Celsius, but remember, that has to be in Kelvin. So we're going to add the 273 to it to make it 295 K. And the question was, what would this gas's volume be at STP, which means our final temp is standard temperature, 273.15 Kelvin. And our final pressure is 1 atmosphere, or anything it's equal to, So we'll make it be the 760 mmHg. And all of this is so that we can get our moles and our liters of H2. That's the name of the game. We want to get our molar volume of our hydrogen. All right, so we take our 726 times our 31.0 times our 273.15 divided by the 760 divided by the 295. And if you do that upright, this gas is going to be 27.4 milliliters at STP. Okay. All right, so we got two of our questions done. Like I said, question one was getting what is the pressure of our gas. Two, just got us what's the volume of the hydrogen at STP. So we are halfway home. We got what we need for the numerator of our problem. Now what we need to do is start working toward the denominator, which is how many moles of hydrogen was there. All right, and sure enough, number 3 comes right out and asks us, what is the theoretical number of moles of hydrogen that can be produced from the 0.028 grams of magnesium? So I know I've got 0.028 grams of the magnesium, and I want to know how many moles of hydrogen is that? And it tells you, refer to equation 1, right, when we do this. And you guys have that from when we did the pre-lab at the beginning. All right, so we're trying to convert grams of Mg into moles of H2. Those are not the same substance, which means this is an identity change. All right, so it's a bracket problem. Just like any bracket problem, start with what you're given. And the first thing we do as quickly as we can is get the thing into moles. So I'll put grams of Mg on the bottom, moles, Mg on top. One goes with moles. 24.31 from the periodic table goes with the grams. Now I'm into moles of magnesium. I want to convert moles of Mg into moles of H2. Right? And from our balanced equation earlier on, and from the one that you see on the front page of the packet right here, you can see that your ratio of Mg to H2 is 1 to 1. Right, so we just do a little bracket problem there. And we take our 0.028 divided by the 24.31. And you get a little number, don't freak out, 0.0016 moles of H2. All right, so we got the two components we need to get the molar volume. Now we just need to do the problem. All right, number 4 tells us to do just that. It says, divide the corrected volume by the theoretical number of moles to get the molar volume in liters per mole. All right, so if we're going to get this molar volume, we need liters of H2. We need moles of H2. All right, from back here, we had our volume, but it's in milliliters. All right, so don't forget you have to divide that by 1,000 to make it liters. So 27.4 divided by the 1,000. So we've got 0.0274 liters. And we have our mole number from right there, 0.0016 moles. So if we take our 0.0274 liters divided by 0.0016, we get a molar volume of 17 liters per mole. And remember, the accepted value for that would be the 22,414, right? We converted it into STP so we could get what we thought it would be. Our experimental was 17 liters per mole, right? And our accepted would be the 22.414. All right, now, what I always do at this point, right, while we're still collecting our gas back there, which I can see is still fizzing away, right, is I let you know in the post-lab which questions match the pre-lab the best. All right, so if we take a look into the post-lab, which starts on page number 6 for you guys. All right. Number 1 says calculate the theoretical moles of hydrogen produced in trial 1 and trial 2. All right, now I'll just have you guys do one trial for the experiment. All right, so if we want to do that, that is going to be a lot like number 3 of the pre-lab. So next to number 1 in your post-lab, I would go ahead and write pre-lab, right, number 3, because that is what you want to follow to get that. All right, now, the one difference in this guy, right, will be that we need to convert, right, our centimeters into grams. All right, so I'm going to give you guys a conversion right there that lets you do that. All right, so for post-lab number 1, 1 centimeter of magnesium equals 0.0109 grams. Okay, so 1 centimeter of magnesium is 0.0109 grams. So your problem is going to start one step before number 3. You'll just convert centimeters into grams. Then you'll do what we did for 3. In number 2, it said calculate the partial pressure of hydrogen produced. This is our Dalton's law problem. All right, so number 2, right, is just like pre-lab number 1. All right, so number 2 in your post-lab is just like pre-lab number 1. All right, number 3 says use the combined gas law to convert the measured volume to the ideal volume at STP. That one, right, is exactly what we were doing right here. So number 3 in your post-lab is like pre-lab number 2. All right, so pre-lab number 2 is going to help you get your answer to post-lab number 3. All right, and then number 4 says divide the volume of the hydrogen by the moles. That one's the first time we match. Pre-lab number 4 is just like post-lab number 4. All right, and I don't know why when we did this, we designed it so that they weren't in order, but this is just to help you keep things straight. All right, and then 5, 6, 7, and 8, those are all new style problems that once you get your answers through the first 4, you should be able to hopefully work your way through. All right, so all I have left to do, and I'm not going to have to post a separate video because I actually had time while the hydrogen was going to show you guys those calculations, is I want to talk about filling in our data table. All right, so you guys can already fill in the very top box, the length of the MG ribbon. All right, my MG ribbon was 3.0 centimeters. All right, so 3.0 centimeters. All right, put a star next to your mass of Mg. You'll have to do a one-step bracket problem like I talked about using the 0.0109 grams to convert your 3 centimeters into how heavy that piece was. Evidence of a chemical reaction. We're going to go back and look at that momentarily. Volume of H2 gas. We're going to go ahead and look at that off the gas collection tube. Corrected volume of H2. Go ahead and put a star there. That's one of your post-lab questions. Temperature of your water bath. We'll go ahead and we'll take out a thermometer and we'll see what the temperature is. And then last but not least, I told you before we even started that the barometer is the 761.3 that you guys see. All right, so let's go to the back, get ourselves some of our numbers, and finish things up. Okay, so if we bring you guys back here, you can see hopefully that most of my tube is now filled with hydrogen gas. And then right down here, you can see we transition to the water. All right, so filling in our table. Your volume of H2 gas. Right? If I'm reading this guy, your volume is looking like 43.6 milliliters. So volume H2 gas should be 43.6 milliliters. All right, and the only other thing we need to do is grab our temperature, all right, of our container. So if I take out my thermometer and put it inside there, and the temperature of the gas and the temperature of the water are going to be the same. Just got to give it a minute to let it reach a thermal equilibrium there. All right, if we take a recording on this guy, I would say that our temperature is looking a whole lot like 24.0 degrees Celsius. All right, so you should have 43.6 milliliters for your volume and 24.0 degrees Celsius for your temperature of your water bath. All right, so hopefully you guys will be good to finish up your post-lab questions. All right, and shoot me a message if you're having any struggles. Other than that, I'll talk to you guys soon.